What is the plus 7 or 6 one?
So you guys are gonna enter in the door, and then there's a stairway, and then you're like, where do I go? Turn left.
Turn left. We'll go.
You're gonna get here, and then here.
So here's the entrance. Okay. And just go down. We'll put some sparkly stars on.
Our first speaker is Evan Bauer, and he's going to talk about diffusion and other mixing for pollution interference in white dwarfs.
I think I need that microphone.
Yeah.
All right, thanks. So I thought I'd start my talk out with a lie. The lie to introduce the topic of polluted white dwarfs is that white dwarfs never show any metal lines in their spectra. In the history of observations of white dwarfs, people were a little bit concerned about this until the original calculations of Schatzmann. He showed actually the surface gravity is really, really high. So we should expect that everything heavy should sink. And so whatever is the lightest element should be the only thing you see in the atmosphere. So that's either helium or hydrogen. Okay, great. So, of course, we all know now that that's not true. There is a large class of white dwarfs called polluted white dwarfs, where you do end up seeing metals after all. But these gravitational settling calculations tell us that there definitely has to be something coming from the outside supplying those metals to the white dwarfs from somewhere. And that accretion is the only reason that you're seeing metal lines at the surface of the white dwarf. So these calculations were pioneered several decades ago. And then over another several decades, this picture emerged that the source of this planetary, or the source of these metals, whatever they are, is in fact planetary debris that is coming from some sort of planetesimals that get disrupted when they are perturbed close to the white dwarf. And they form dusty debris disks. And eventually these metals accrete onto the surface. And so the fact that you're seeing these metals in polluted white dwarfs can actually tell you a lot about planetesimals and planets around white dwarfs, what they're made of, their compositions, and it turns out that they're mostly rocky. Okay, so just to sort of go through a quick example of what you can infer with a polluted white dwarf. Here's an example of a MESA model for G29-38. Where you can do the detailed diffusion calculation, and you get a diffusion time scale of roughly a year. And so what I'm showing here is just a simulation in which accretion happens for 10 years with a variety of metals that are observed in the atmosphere of this white dwarf. And then I turn off accretion in the MESA model just to see that these things exponentially decay. And this is actually a calculation you can do analytically. So I'm just showing you can match the analytics with a MESA model if you have accretion and diffusion and all the physics that you need to do. And you can make inferences about the accreted material, how much accretion, how fast the accretion needs to be to match the observations, and the relative amount of accreted material. So there are some corrections to be made for different diffusion timescales of different metals. So you'll notice if you look closely, or I guess I can just tell you, iron and oxygen in this model are being accreted at the same mass fraction, but since iron sinks more quickly, it approaches a different equilibrium and you end up seeing more oxygen, according to this calculation. And so once you correct for those diffusion timescales, then you would say, in fact, that you're accreting the same amount of both of those metals. Okay, so if we switch from one object to lots of objects, I can tell you about a sample of lots of hydrogen atmosphere white dwarfs with evidence of calcium. That's one of the easiest elements to see. And if I make the assumption that calcium is present in roughly bulk earth proportions, so it's actually going to carry along other metals with it at the ratios of bulk earth, and I just calculate a total accretion rate, this is the result I get. So these are my own calculations with MESA models. They agree pretty well with some of the classic calculations of Detlef Koester and others. So we have some distribution of 30-some accretion rates over a range of effective temperatures just from these calcium observations. So really quickly, I'm going to rescale this axis because I'm going to start putting more points on it. So here's a different population of calculations I haven't done. I got these from Jay. Thank you, Jay. And these are helium atmosphere white dwarfs, where somebody else did these accretion rate calculations. And the interesting thing is they sort of show a distribution that gets up to several orders of magnitude higher accretion rates. And so really the process that supplies accretion to polluted white dwarfs shouldn't know whether it's a helium atmosphere or a hydrogen atmosphere. The stuff's coming from outside. So it's a little concerning that these populations don't totally agree with each other. So now I'm going to skip to the punchline of this talk right away, which is I'm going to adjust these points that I showed from my MESA calculations to include an additional source of mixing. So in these helium atmospheres, I'm going to say, I'm going to turn on thermohaline mixing in MESA models and then recalculate or re-infer the accretion rates. So I get a way, way different answer, several orders of magnitude higher for hotter white dwarfs. And I guess I'll leave it to you to decide whether I have solved this problem of the discrepancy in accretion rates, because on the one hand right here, they start to match really well, so that's nice. But then I have huge accretion rates at the very hot end. So maybe I'll come back and discuss that at the end. But I want to talk about what is this thermohaline instability real quick. So I would say this is a known fluid instability that's been studied in astrophysical contexts for a long time, but it was only pretty recently that it was first applied to polluted white dwarfs. Basically, the instability involves, it's called double diffusive because you need to have diffusion of heat in a fluid element for this instability to kick in. So sort of if you think in terms of classic convection criteria in stellar evolution, you think I take a fluid element and if I perturb it adiabatically, so it doesn't do any thermal transport with its surroundings, it will change its temperature and density in an adiabatic perturbation, and it could end up running away. And so you can check that criterion and say, is my star convective or not? Thermohaline is similar, except there's also another diffusivity to check, which is instead of adiabatically perturbing a fluid element, I let it do some thermal transport with its surroundings. And so if I take something that's hot and dense, it would be stably stratified, but if it cools off, it discovers that it's overdense and it can sink further, and that will lead to lots of extra mixing. Okay, so this is sort of the mathematical criterion that you can write down to decide if a fluid element is in fact going to be thermohaline unstable. So maybe we don't need to dig into the details super carefully here, but this plot is just meant to convince you that this criterion for instability is actually satisfied by many orders of magnitude. So I'm going back to this particular model of G2938 that I showed you earlier, where I did the diffusion calculation and I matched the abundances and I said we could infer an accretion rate from that. But I have a metallicity profile here in this orange line. And if I look at sort of the composition gradient that will lead to this thermohaline instability and check this criterion, then it satisfies the criterion for thermohaline instability. And so it needs to experience this instability. And if I turn on mixing that's associated with that instability, then the metals mix way, way deeper into the envelope. And I need to turn up the accretion rate to continue to match the observed abundances. So I infer a higher accretion rate by, for this particular object, just about 1 order of magnitude. But if I start doing a large range of parameters with MESA models, then I can actually get a several orders of magnitude correction. So this is an example of a grid of MESA models that are all at 11,000 Kelvin. And so basically what I can do is I can accrete bulk earth material in a MESA model at whatever accretion rate I want. And if I'm at a low accretion rate, the thermohaline instability doesn't kick in and I match the diffusion calculations. But as the accretion rate goes up, the metals excite the thermohaline instability. And then the observed amount of calcium at the surface ends up being a lot lower than what you would infer for a given accretion rate with diffusion alone. Or the other way of saying that is if I'm at a particular abundance on this y-axis and I project over to where I would hit a total accretion rate, I'm going to infer a much higher accretion rate at a given observed value. Okay, so I can do this actually for not just a grid in accretion rate, but a grid over many effective temperatures. So this is just showing an example of few effective temperatures. And the method that I'm going to use to infer accretion rates then is to interpolate in this grid. I actually have lots more effective temperatures, but the idea is I can interpolate in an observed calcium abundance in both accretion rate and then across effective temperatures to match the observation and then infer a total accretion rate. So this is the result I showed you earlier, just going back to it. So there's definitely a much different trend. The accretion rates are much higher. And this corresponds to a much higher amount of mass being accreted, especially at these earlier times as the white dwarf cools. So I think if this is correct, then the picture of accretion happening in polluted white dwarfs is a lot different than what we've been assuming before. So just a few quick conclusions. I want to emphasize that I'm not the only one that has obtained results like this. There are other codes as well. So this includes the La Plata code, where they've included a version of thermohaline mixing. And they've done a few objects and tend to agree roughly with the MESA results. The new result here is more that there's a large parameter space being studied. But I think in general, this particular implementation with MESA is fairly conservative on the amount of mixing, and we still see a really large effect. And since we're seeing this with multiple codes, I would argue that it has to be real unless we can invoke some other sort of physics to prevent the thermohaline mixing. So then I'll just leave you with a couple interesting puzzles or implications. So if this is true, one of the fun results would be that these high accretion rates should probably or maybe definitely lead to observable X-rays. So one way you could falsify this result is if you went out and looked at all the polluted white dwarfs for which we're inferring high accretion rates and say there are no X-rays to see. So I think Jay is already working on maybe trying to prove me wrong in that way. And then the other puzzle, I would say, is the classic physics that's been invoked to get material to the surface of polluted white dwarfs is Poynting-Robertson drag. But there's actually an upper limit on the accretion rate that can give you, and that's way down here. So the physics, whatever's going on in the disk that gets the material to the white dwarf is way, way different with these accretion rates. It's probably dominated by viscous spreading. So I think we'll need to rethink that as well. But I'll stop there. Thank you.
We're going to have 2 more speakers before questions. Our next speaker is Florian Sostinger.
That's right, yes.
Okay. And he's going to talk about high-resolution simulations of DA white dwarfs, DA white dwarf surface convection, sorry.
Okay. Hello, everyone. My name is Florian. I'm located at that university where the name spans about 2 lines. We are a small university in the far east of Germany, and the collaborators are Mike Montgomery and Friedrich Kupke. Well, you may wonder about the screenshot behind of the lines here. Yeah, it is science. It's not inspired by Austin Powers. I will come back at the end of my talk what's going with that simulation here. The background of this talk are settling rates. So we have the evidence that in about 25% of all DAs, we have metallic lines of calcium or magnesium. And well, that's quite unusual, as we have heard in the talk previously, because these heavy elements should sink down to the core. So that implies that we have at first some accretion process going on, and on the other side, there has to be a much higher settling rate than assumed. So in order to calculate the settling rates and the mixing there, we are doing 3D simulations and determine the settling rates by measuring at the bottom of the convection zones. So we are including photosphere, convection zone, overshooting, and radiative zone in white dwarf simulations. We do this with Antares, not the star. It's a numerical tool for astrophysical research. And this is in 3D numerical code, which exists since 10, 15 years. And we are doing convection simulations for the sun, A-stars, Cepheids, semi-convection, double diffusive convection, and so on. So in the previous version, the sketch here, everything was red and yellow from the sun, so I colored it in blue, divided all length scales by 1000, and we have the white dwarf. Well, it's not that easy, but in principle, the code works quite good for white dwarfs now. We have an MPI implementation and OpenMP. That means the code works on up to 2000 cores. However, it takes at least 2 months that we get a very nice simulation. Yeah, that's a mugshot of the simulations we have done so far. We have a grid of about 10 effective temperatures, starting from 11,600 up to 13,400 for log G of 8. And here you can see a horizontal slice in temperature on the surface. Red means we have hot regions and blue means we have cold regions. And you see there that the structures are very fine for the colder temperatures and got very big one for the more radiative stars. Our case study, or I like to say here our Drosophila, is the 11,800. We started that case about 1 year, and we published it here in EMRAS. Our 3D simulation covers a region of about 15 square kilometers, and the height of the box is about 8 kilometers. And we usually try to that each cell is less than 30 meters, so really high resolution in that sense. We are calculating everything in sound crossing times, which is about 0.2 seconds from the bottom to the top of this box. And typically, a 3D simulation is relaxed after 18 seconds, so 90 or 100 sound crossing times. So that simulation took about 2 months on around about 600 cores. Yeah, quite resource intensive. That's a nice movie here. So here's the horizontal slides on the temperature. That's a vertical velocity field, and here's some stuff from the radiative transfer, so the vertical radiative flux. And you see quite nice in seconds here the structure of plumes forming here. So red are updraft and blue are downdrafts. But yeah, this is just for the audience, so we cannot work with that in the paper, so we have to do statistics. The next question is, when is a simulation converged? We have several timescales in the simulations, and the longest one is, of course, the thermal relaxation timescale. But we have to wait on around about 1,000 seconds for that, but this is not possible to do with 3D simulations. So we set our limit that the input flux versus the output flux on the top maximal differs by 4%. You see this here. So in terms of sound crossing time, we plot the scaled output flux on the top, and after about 90 sound crossing times, you see that we get under 4%, which is quite good to do statistics with that simulation. What about the velocities? if you calculate too short, we get massive problems with the velocities. That's on that axis, you see the vertical depths in kilometers and the root mean square of the velocities on the y-axis. And as you can see here, if you just calculate 30 to 40 sound crossing times, that means 10, 20 seconds, or 10 seconds roundabout, then all velocities are much underestimated. So you have to calculate much longer that these velocities converge until they reach their maximum or they converged value. So everything has to be done for around 90 sound crossing times that you can do correct statistics. These are two cases. One is the 11,800, the other one 12,400. And you can see here the fluxes. So this orange line is the normalized total flux. And here's the convective flux, kinetic flux, and radiative flux. And if we want to determine the convection zone and the overshooting zones, it's quite easy. So convection zone is given by the superadiabatic gradient and the overshooting region here where all the fluxes go to zero, except the total flux, of course. And as you can see, the overshooting region in the cold case, or in the case where it's 11,800, is much bigger than in case of 12,400. A very good indication for the overshooting region is this value here, the kurtosis. It is the force momentum, and it just says that we have some infrequent events, but they are massive. And that means we have big plumes penetrating into the overshooting region. And we are using both plots to estimate the overshooting region. That's in comparison of our results with MLT alpha and results by Tremblay. Especially the 13,000 K case is very interesting because it's a quite good test for the radiative transport. That means if our hydrodynamic doesn't work perfectly in that region, we wouldn't get that good fit. And as you can see, alpha, yeah, it differs, but it's in between 20 to 18%, and usually depends on the initial model and opacities and so on. But it's quite good from the comparison. Additionally, we found P modes in our simulations. Well, they do not contribute much to the mixing, but to the velocities. And the P modes are located or are found beneath the overshooting region. So that's the bottom of the overshooting region. Here's one small plume left, and this could be a small plume. And below, we only have a very small temperature fluctuation region, but here we have P modes. That means these P modes have a frequency which is more or less the sound crossing time in our box, but they do not contribute to mixing. What else? Yeah, we found some that the decay of the velocities are not logarithmically, but they are linear. That has a very strong influence on the mixing region, because when we take the logarithmic fit, then the mixed mass is quite much bigger than if you take a linear fit, but that's only a detail for the settling rates afterwards. The settling rates itself, if we calculate it with convection and overshooting, are about 78 times higher than only by convection. So here is the result per Custer. And in that movie, you see we add some particles at the top and at the bottom, and you see that these particles move along lines here, and these lines are interestingly minima of the vorticity. So we have some things like these points here where the particles stay a very long time. But I think you will see more results about that in the next talk. We found that including overshooting, the mixed mass is around 300 times higher. That means all the settling rates and so on are higher too. Yeah, and at the end, I want to show you the closest look on the white dwarf so far. It's a numerical simulation with a cell width of around 5 meters. It's not turbulent, okay? It's laminar. That means the Reynolds number is very low. We are not able here to calculate with realistic viscosities. But what you can see is the impact of the compressibility. You see these waves here, these are shock waves. And they contribute to mixing and heat up the fluid. So we see regions in the photosphere where the temperature goes down to just 4,000 K. Thank you very much.
Okay, next speaker is Shane Cunningham, and he's going to talk about investigating convective overshoot in white dwarfs.
Here, sorry. We can speak Spanish. Okay.
How's that?
Calm down.
Okay, thanks. So I'm here from the University of Warwick, and I'm going to present to you research we've been carrying out trying to characterize the mixing efficiency due to convective overshoot in pure hydrogen atmosphered white dwarfs. I realize I have no laser pointer in my hand. So Evan motivated nicely the impact or the necessity to understand diffusion inside the white dwarf atmosphere. And we've seen some nice 3D simulations from Florian. So as we've already seen, the elemental stratification of the white dwarf coupled with the observed heavy elements in their atmosphere provide evidence, and have done for the last 100 years, that white dwarfs are accreting material from their surroundings. We can infer from that accretion rates, but to do that, we need to know precisely the observed abundances of any given metal and the volume over which that abundance is prevalent. That's the focus of my research. So as a white dwarf cools sufficiently, it will develop a convection zone. And it's well known that in the fully mixed region, material will be mixed almost instantaneously. And that's covered quite well by the 1D mixing length theory. However, there's some physics which is missed by 1D mixing length theory, and that's the focus of this talk. I'm showing here a slice from our 3D simulations where I've got convective velocities shown in white. The 1D convection zone, the most crude implementation of the mixing length theory, would be here in green. So this shows quite nicely that we have sufficient motion beneath this region. The reason for this motion is that in the convectively unstable region, material is accelerated close to the boundary. It then has sufficient momentum to travel quite far down into the white dwarf atmosphere. This process is known as convective overshoot, and it's the focus of my research to characterize how efficiently this region mixes material. So we do that using a trace plasma. I'm showing here a massless, non-interacting trace particle plasma. So it does feel no gravitational effect. It's subject only to the local velocity fields. So what you'll see is that gradually it starts being affected by some of the deeper plumes once they reach it. I'm evolving the simulation here at 1/4 of real time. Now let's look at what happens when we put the plasma higher up into the atmosphere, closer to the unstable region. You'll see that it mixes much more quickly. And that within about 3 or 4 stellar seconds, we have an almost homogeneous mix within the convectively unstable region. So our work sets about quantifying the efficiency of this diffusion as a function of depth. We do this by computing a diffusion coefficient. For a 1D diffusion problem, we can say that the mean square displacement is equal to twice the diffusion coefficient times time. So I'm plotting here in black crosses the diffusion coefficient for a simulation at 13,500 Kelvin. The purple dash shows the vertical root mean square velocity profile. And you see we've got the core to the right. So you see the velocities are decaying as we move towards the core of the white dwarf. In blue dot dash, I'm showing the square of that profile. So I want you to notice that the diffusion coefficient is qualitatively bound by those two quantities. We've done this for 2 other temperatures at 12,000 and 13,000 Kelvin, and we find qualitatively a similar result. To the left of each of these plots, we have the convectively unstable region where it's futile to compute a diffusion coefficient because we know it mixes very quickly. But we predict that there will still be mixing happening beneath this, but currently it's not accessible to us to compute a diffusion coefficient due to the presence of waves in the base of the simulation. And Florian already alluded to that from his simulations. So I'm plotting here a 2-kilometer vertical extent, through the simulation. So now let's look at the full extent of the simulation box. So this is now the full extent of our simulation, which is 10 kilometers. This is at 12,000 Kelvin. On the x-axis, I have for the people at the back, it's in mass fraction. So the mass above divided by the total mass of the star. And to fully understand the journey a trace particle will take through the atmosphere, we need to connect convective velocities to microscopic diffusive velocities. So in blue dash, I'm plotting here velocities from Detlev-Costa for magnesium, calcium, and silicon. So you can imagine a white dwarf, it's not a white dwarf, a trace metal will arrive at the surface, be subjected to some convective velocities, and eventually be subjected to the next dominant mass transport process due to gravitational settling and thermal diffusion. So the 1D picture would look something like this in its most crude implementation. You have a convectively unstable region, and at the base of that, you have no more convective information. So you could, in the most naive sense, say that this is the base of the convection zone. But what should be obvious is that we have a massive discontinuity in the velocity profile of 7 orders of magnitude, which obviously does not seem too physical. The diffusion coefficients I just showed were for this blue region. So I hope I've convinced you that at least we can say that we know that the blue and the green bit are fully mixed. But we think we can do better than that because we have waves in the base of our simulation which disrupt our computation of a diffusion coefficient in this region here. So the waves manifest, I'm not going to attempt to point because I'll probably kill the PowerPoint presentation, but the waves manifest as the upward inflection between the blue and the purple region. We don't expect that upward turn. That increase in the velocities is from the waves. So we've got standing waves trapped in the base of the simulation. And they're driven physically by the motion of the convection zone, but they're augmented by the box boundaries. So that they are born as something physical, but not a good description of the waves we expect to find in a white dwarf. So to come up with a more conservative estimate for the base of the mixed region, we can make use of something that's quite nice. Here I'm showing the vertical velocities in a horizontal slice. And this horizontal slice is exactly between the blue and the purple. So the overshoot fingers, we still have some of the deepest plumes there, and they manifest as those really small circles. Whereas the waves manifest as that large structure which covers the full extent of the box. So because they have such different spatial extents, in the power spectrum here on the left at the bottom, you see that the waves occupy the low K number, and the overshoot plumes occupy the high K number, that second peak you see around 10. So by creating a high-pass filter, we can essentially try to remove the contribution of waves from the velocity profile and come up with something that looks more like what we would expect if there were no waves. Now, there probably are some waves, so we think this is a conservative estimate. So I'm showing here an increasing orange, higher and higher cuts in K-space. So what we would like is that we have a deep enough simulation that eventually these velocities decay below the diffusive ones. But that's computationally very expensive and currently out of our reach. So the next best thing that we can do is to extrapolate the linear profile which the filtering naturally converges to. So we would say that this is now the base of our convection zone, or at least the base of the mixed region. And so you see that this corresponds to an increase in mixed mass by 2.5 orders of magnitude, but a decrease in the diffusion velocity by an order of magnitude and a half. So this is just for a simulation at 12,000 Kelvin. And so naturally we want to probe a wider parameter space. So we've computed a grid of 15 fully convective simulations from 11,400 up to 18,000 Kelvin. I'm showing here on the top in purple, blue, and gray, 1D and mean 3D convection zone bases. And on the bottom, I'm showing our overshoot corrected convection zone bases, or fully mixed region bases. So for the majority of our grid, we find an increase in mixed mass of 3.5 orders of magnitude. The blue line corresponds to the model that Florian just presented. So the predictions from the Kupka group for their 11,800 simulation. So we find that we're in agreement with the upper end of the overshoot correction. So let's look at what this looks like for accretion rates. Here I'm showing in the 1D mixing length theory accretion rates. And in orange, the accretion rate when we include convective overshoot. So we see that for the majority of our grid, we get an increase of about an order of magnitude for DA white dwarfs in the temperature range 12,000 to 16,000 Kelvin. And it kind of tails off at either end. So I was heavily inspired by Evan's paper earlier this year, where he and the plot that he just showed, where he corrects the thermohaline mixing. So I thought I'd try and do something similar myself with our overshoot correction. So this is a sample taken mostly from J, but it was published in the Berg-4 2014 paper. In blue, we show polluted dBs, and in black open circles, polluted DAs. I'm showing the correction, the inclusion of the overshoot correction to the DAs. So there's no correction being applied to the dBs. We would expect there'd be something, but probably not as much as the DAs. We also have no correction below 11,000 Kelvin, where our grid stops. There should be a correction there too, and we're working on an analytic description of that. To make it maybe a bit more obvious that it has done something useful, I'm showing here in blue the mean accretion rate for the dBs, and in red the mean accretion rate for the uncorrected DAs. And this is what it looks like with the correction. So to my eye, it looks like they come into closer agreement. I don't think, but it's definitely not the end of the story, but it's a demonstration of where we might be able to go with this. So I shall leave my summary slide there and take your questions.
If you have questions now, I invite the other speakers to come. Jay? Great.
Well, my question for Evan, but I guess Tim, if you have any thoughts, that'd be interesting. So Jonathan Gerber was the first person to notice that once we started calculating the accretion rates in a uniform manner, mass in the outer layers divided by the sinking time scale, that the helium stars appeared to have higher rates. And we eventually, I think we had at least a self-consistent explanation. That's because averaging that measurement over these very long sinking time scales in the helium stars, you might be missing the rates going up and down. You just see one value. So you're missing the short high rate bursts in the DAs was the idea. So now you have flipped it where you partly solved it, but you have a similar problem. So now you have very high rates in the DAs. You have nothing corresponding to that in the helium white dwarfs. Do you have an idea for how that gap might be closed? Some kind of physical accretion or something in the stars, such as we've got sinking time scale bombs?
Yeah, okay, so I think definitely there's a lot to think about there. I think none of us actually sort of proposed any correction to the helium atmospheres yet, but I think there are going to be overshoot corrections potentially, maybe a little bit of thermohaline mixing, and my instinct, I guess, is that there are more corrections to explore in the case of dBs that will move the accretion rates for those up.
Next question, here, Manuel.
My question is for Evan, but given what Florian and Tim have discussed, so given turbulence in the convective zone, how safe is the determination of the mu gradient or the abundance gradient that will play a role to say about the efficiency of thermal mixing?
The abundance gradient in the convection zone?
Well, the abundant gradients that will say about the efficiency of thermal mixing, the relevant section of the bottom of the convection zone.
Yeah, oh, okay. So there is, I think that's a time-dependent process. What happens is the thermohaline mixing region extends pretty far past the convection zone. So eventually it forms kind of an extended abundance gradient. It's not really sensitive to what's happening at the very edge of the convection zone.
This is probably a question for all three of you. Would overshoot destroy double diffusion?
Okay, I'll start. I've started to explore that in MESA models with nothing nearly as sophisticated as I think the more realistic overshoot that either of these guys are doing. I would say there are some models in which that would be the case, that it would extend the mixing region to be large enough that it would dilute the metals, and then there wouldn't be much of a concentration gradient. In others, there can be thermohaline mixing even beyond a pretty large overshoot region.
I just want to comment this, that depends mainly on this density ratio and the value of density ratio, which is the superadiabatic gradient over the molecular weight gradient. And it's always this, if it's below 1 or bigger than 1, then the efficiency is determined with that value. So without having that value, you cannot say if it's if overshooting is influenced or not.
I have a question to Florian about the radiative transfer in these models. How is that handled? Is it similarly as in the cobalt code by Ludwig, Freitag, and Steffen, or also with multi-frequency bands and so on?
So we are calculating with gray with a short characteristic method in the top 20% of the zone. So we have a transition zone at around about 100 of the optical depth, and below there's the diffusion approximation. And we are using in the 3D models 34 rays.
And with different frequencies?
No, it's gray.
So it's gray. And don't you think that this may be a shortcoming?
Of course, but then you have a fourth time calculation of everything.
JJ is pointing to someone. Please, that someone raise the hand.
Evan, you alluded to this in your talk. If you increase the accretion rates to the level that you're suggesting in the DNs, of which we see a large percentage currently accreting, there's serious implications for where this mass is coming from. I think the highest level on your plot looks to be an accretion rate of around Earth mass every million years. So do you think it's more likely that you guys have got more work to do in your atmosphere models, or that we're missing something fundamental about solar systems of these progenitor stars, which are not otherwise well known?
So I think last time I checked, it's not quite that high, but you're right that the total amount of mass is approaching around an Earth mass. And so I think the models would imply that there needs to be a lot more mass around these systems than we've previously inferred. Might not want to speculate too much beyond that.
Another question? Yeah. Okay, let's thank the speakers again. Our next speaker is Ingrid Pelissoli, and she's going to tell us if the SDA puzzle is solved or not.
This is not an ideal setup for someone with Italian blood, but I'll give it a shot. So my name is Ingrid Pelissoli. I'm a postdoc at the University of Potsdam. And today I'm talking to you about the SDA puzzle, which we first introduced in the last White Dwarf meeting. And I'm going to show the developments in the last 2 years, especially given the Gaia data release 2 data. So first, let me introduce how this puzzle came to be. This is the White Dwarf mass distribution for the A's in red and the B's in black. And here we have an upper limit at around 1.4 solar masses, which is expected because it's simply the Chandrasekhar mass. And we also have a lower limit here at around 0.3 solar masses, which is the single evolution limit given the age of the universe. A progenitor that would lead to a white dwarf mass lower than that has an evolutionary time in the main sequence longer than the age of the universe. However, over 50% of stars are in binaries, as Silvia already told us, and around 25% of those are expected to interact. And depending on the efficiency of mass transfer in this interaction, this can lead to a common envelope that can lead to an enhancement in mass loss and can generate white dwarfs below the single evolution limit. These objects are known as extremely low mass white dwarfs, and quite a few of them were found in the ELM survey by Brown and collaborators. This ELM survey was kind of a spin-off of the hypervelocity survey. So what they did was a color selection, and they observed the stars in this region here to verify that they were in close binaries and obtain a mass estimate. And with that, they found about 80 ELMs with the log G between around 5 and 7.5 and temperatures between 8 and 20,000 Kelvin. You can see some models here in the background, and these models also predict objects below this limit and cooler than this. Especially in temperature, we predict that the objects spend around the same amount of time below 8,000 Kelvin and above that. So we should expect the same amount of objects in this region, which is not even in the graph, and this region over here. And this is not the case in the ELM survey, mostly because they did a color cut. So although the ELM survey is mostly complete within this region, we should still expect to find objects which are cooler and also showing lower log G. So how can we find these objects? The spectrum of an ELM object looks basically like a main sequence A-type star. So we have the Balmer lines, and as they have a lower log G, they are somewhat narrow. And in fact, the SDSS even classifies a few of the known ELMs, like this one, as A-type objects, main sequence A-type objects. So instead of doing a color selection, we decided to select ELM candidates by doing a spectral selection. So we retrieved every object in the SDSS with type O, B, and A, which show hydrogen-rich atmospheres, just like the ELMs. And that fitted all the spectra with solar abundance models. The results are here. These objects, O, B, and A type, are in black. The objects from the ELM survey are the red triangles here for comparison. I also put some DAs down here. These models in blue are the binary evolution models from Aline Strate, and I also put here some single evolution models for you to see that these objects are not explained by the single evolution models, but they can be explained by binary evolution. So we were quite surprised at this result because we actually have hundreds of objects below this line here, which is the upper log G for main sequence A-type objects. Even for very low metallicity, they cannot have a log G above around 4.75. If we assumed pure hydrogen atmospheres, we had thousands of objects here. And that's much more than we were expecting, given the null population of 80 objects. So instead of calling all of these ELM or anything, we gave this a spectral classification. So we call these objects SDA stars. But I caution that calling an object an SDA star doesn't mean that is an ELM. I'm not saying that they are not main sequence objects. I'm only saying this is a spectral class. They have A-type spectra and log G that is mostly below the main sequence, so SD. But they have an unknown evolutionary origin. In fact, there is evidence that they have more than one evolutionary origin. So I'm showing here the reduced proper Marshall diagram for the objects in my sample. So this reduced proper Marshall diagram is kind of a proxy for absolute magnitude. The objects are here. This is a 2D histogram, and the non-ULMs are in green for comparison. And you can see that the SDAs can be broken into two distributions. There's this blue distribution here that shows quite a lot of intersection with the distribution of the non-ELMs. And there's also this red distribution here that doesn't show a lot of intersection with the non-ELMs. And we suggested that this red distribution is composed by objects that are actually of later type than A, so they are cool objects, but they are metal poor, so they look like A-type simply because they don't have any metals. This was first suggested by Warren Brown to explain all of the SDAs, but apparently it can explain only a fraction of them. And the LMs we were looking for are probably in this blue distribution here. We were expecting that the Gaia data would help us disentangle these two populations. So here's Gaia's view of our sample. I'm showing here only objects with parallax over error above 4, and I also did some other cuts that I can discuss later. So the SDAs are in blue, the non-ULMs are in green, and here in red is the sample C of Lindegren et al. 2018, which is mostly objects within 100 parsec of the sun. So let's zoom in the region of the SDAs, and it does indeed appear that many of them are below the main sequence. So they are mostly between main sequence and white dwarf, and they are close to the elms, below the main sequence, so maybe they are not main sequence. Well, as I said, this is solar neighborhood, whereas these objects, they have very low metallicity. So let's compare, oh, and also they are mostly in the halo, given the Gaia distance. Most of them are more distant than 2 kiloparsecs, so we cannot compare them to solar neighborhood. So we compared them to isochrones for 10 gigayears, which is more or less the age of the halo, and low metallicity. And we can see that most of them seem to be consistent with this low metallicity isochrones. So the conclusion here was that most SDAs seem to be indeed consistent with old halo metal-poor stars. These isochrones indicate that they have a mass below 0.9 solar masses, otherwise they would have evolved off the main sequence, and temperatures between 6,000 and 8,000 Kelvin. So they are nothing like the A stars we are used to. As I said, they only look like A-type stars due to the lack of metals. You might be thinking that I was sad with this result, I don't have that many elms, but actually I was betting on that, and I won. So I didn't have elms, but I had beer, so I was fine. But again, most of them are consistent with main sequence, but not all of them. We still have a few ELMs in there, and how can we dig them up? What I did was a radius estimate following the same approach that the Gaia collaboration did, but we have the advantage that we have spectra, so we could obtain the temperature from the STS spectra, and we also took care of propagating every uncertainty via Monte Carlo. So here is the radius estimate for these objects as a function of temperature. And the important thing here is that main sequence stars, they show a minimum radius, whereas during the revolution, ELMs and the precursors, the pre-ELMs, they can show basically any radius. So anything below this line, which is the minimum radius for main sequence, cannot be a main sequence object. So we see that there's still a lot of objects there. Well, but we have to take uncertainties into account. So assuming a 99% confidence level and 5% uncertainty in our spectroscopic temperature, we have about 150 objects in this region that have to be PLMs and ELMs. But this assumption on the temperature leads to this weird blob here, very close to what we think is the main sequence. And at lower temperatures, our uncertainty can actually be a bit higher. So assuming a 10% uncertainty, then I get around 50 new ELMs and pre-ELMs. That's more than a 50% increase in the non-sample. And it's really good because they show lower temperature and low log G, which is exactly what we were looking for. So to summarize all this, like the content of the universe, we don't know very much about most of the SDAs because only 10% of them have good parallax estimates on Gaia. And out of this 10% that we know, most seem to be consistent with halo, metal core low mass stars, but a sizable fraction of around 5% do show already that cannot be explained as main sequence stars. So they are ELMs and their precursors. So we have to keep an eye on these SDAs and do not ignore them because we are missing some PLMs there. So answering the question of my title, is the SDA puzzle solved? Well, not entirely, but we are certainly getting there. Thank you.
We are having one more talk before questions.
The greatest one. Okay. This is this I put.
Our next speaker is Monika Sorotovic, and she's going to tell us about the origin of single low mass white dwarfs.
Yeah, excuse me. So this one is for what?
For the stream.
Okay. Yeah, thanks. So, well, these are, well, first I have to introduce what means by low mass white dwarfs, because these are not extremely low mass white dwarfs, but are all the white dwarfs with masses below around 0.5 solar masses, which are supposed to have helium core white dwarfs, to have helium cores. So first, looking at the observations, we see that in our neighborhood, around 10% of all the white dwarfs that we observe are supposed to have masses below around 0.5. This is from Kepler. And typically, all of them, or most of them, are found in closed binaries, because you need a closed binary to interact with the progenitor of the white dwarf to generate such a low mass. However, there is still a fraction of around 20 to 30% that seem to be single. If you combine these two fractions, 20 to 30% of this 10% of helium white dwarfs, you get that around 2 to 3% of all the white dwarfs in the solar neighborhood seem to be single low mass helium white dwarfs. So where do they come from? They cannot have formed in normal single star formation, because the evolutionary timescale for this is longer than the Hubble time. So many channels have been proposed to explain this, mainly taking into account mergers, these two extreme mass loss on the FGB, or also that these are the remnants of type 1a supernova. So I don't have here time to go into details of all this. You can see a review in Sorotovic and Schreiber 2017. But as a conclusion, none of this, or not even combining all of these channels, we can get enough single low mass white dwarfs to explain the observed fraction. So as a summary of this, we have too many single low mass white dwarfs that we cannot explain. On the other hand, as Anna Pala told us on Monday, in cataclysmic variables, we have the opposite. We predict too many low mass white dwarfs that we do not observe, and the observed white dwarf mass distribution peaks towards higher masses. If you compare with their progenitors that are post-common envelope binaries, you don't see this problem. You see a lot of low mass white dwarfs that are consistent with predictions. So what happened to them when they become CVs? So in 2011, we demonstrated that this was not an observational bias. In fact, if there was a bias in the new data, it was against high mass white dwarfs, and we see a lot of them. And this also demonstrates that it's not related to the common envelope phase. So CVs are more massive, the white dwarfs in CVs, than what expected. So we proposed at that time that mass growth could be an answer, either during the cataclysmic variable phase or before, in a previous phase of thermal timescale mass transfer. However, in 2015, with Weinen, we demonstrate that this was also not a solution. So even if we accrete all the mass of the secondaries, we cannot reproduce the distribution of white dwarf masses, and we also introduced more problems between CV models and observations. So in summary, we have too few low mass white dwarfs in CVs and too many in single stars. So we decided to prove, what if all the systems here merge when they become CVs, and they this can explain the absence of low mass white dwarfs in cataclysmic variables and the existence of single low mass white dwarfs. So to test this, we decided to review the stability limits for mass transfer, for stable mass transfer in cataclysmic variables. You can obtain a critical mass ratio for stable mass transfer by equating the adiabatic mass radius exponent with the mass radius exponent of the Roche law of the secondary. And this one is strongly dependent on the angular momentum laws that you assume. So here I have to distinguish between two types of angular momentum laws. One is called systemic angular momentum laws, and it's not dependent on mass transfer. So it's the angular momentum laws that you will also have in a detached system, that is magnetic braking and gravitational radiation. And consequential angular momentum laws is the angular momentum laws that is generated by mass transfer itself. So the old simulations typically use either the fully conservative case, where no mass loss is assumed, which we know is not true because you have no eruptions in cataclysmic variables when you lose material. And the other one is a classical form of consequential angular momentum loss that assumes that the specific angular momentum of the ejecta equals the specific angular momentum of the white dwarf. So friction and other things are ignored. Here you have the simulations. This is a mass ratio versus secondary mass of cataclysmic variables. The light blue dots are the simulated systems, and the black dots are the observed ones. This is the fully conservative case, and the classical, the ones that include classical consequential angular momentum loss. This region are the regions of unstable mass transfer, so systems that are on this region merge. This line here is the average for the observed white dwarf mass in cataclysmic variables, which is around 0.83. And this other line is the line of 0.5, which marks the limit between helium white dwarfs and carbon-oxygen white dwarfs or oxygen-neon magnesium white dwarfs. So if you go up in this, up and left to this diagram, you go towards lower white dwarf masses. So here these are the observed white dwarf mass distribution that clearly disagree. The simulations here in dark gray, sorry, the observations in dark gray with the simulations in light gray. So you see clearly here that the problem is here because we have low mass white dwarfs with very low mass companions. So it was, if we have plotted this before, it was obvious that mass growth was not going to solve the problem, because even if you accrete the whole companion, you still have a low mass white dwarf. So this limit here, it's more relaxed. So including consequential angular momentum loss is even, the problem is even worse. You get more low mass white dwarfs. And this is because, yeah, you have more angular momentum loss, so the system gets closer to faster, but also the white dwarf mass is reduced, is losing mass, the white dwarf, because of the nova eruptions that was not taken into account here. And this compensates the effect of the extra angular momentum loss because you have a reduction of the Roche law of the secondary that is smaller, slower. So we decided to kind of artificially eliminate all these systems by setting, well, I need to get rid, that's what I said, by setting a consequential angular momentum loss form that is inversely proportional to the mass of the white dwarf. So we set this and we put this limit here. Well, we did a lot of Monte Carlo simulations, and we, with the KS test for the cumulative distribution of white dwarf masses, we fit the best parameter here for having a similar distribution to the observed one. And of course, we managed to get a very good agreement between observations and simulations for the white dwarf mass distribution, because this is what we were looking for. But this model also fits better the observed orbital period distribution and the space density for CVs. Now, this model was not like invented from somewhere. It was motivated by the fact that we had to eliminate the systems there, but it has some physical explanation behind. That is something that we want to introduce in new models that remove the empirical fit by something more theoretical, and that is friction. Friction was normally ignored in all the models for cataclysmic variables because it was supposed to be very small, the amount of angular momentum that you take away because of friction. And this is because when you have high ejection velocities, then friction is small. Here you can see that the specific angular momentum that you take away for different mass ratios depends strongly on the velocity of the ejecta and can go to very high values when you go to the slowest ejections. And in massive novas, you normally see high velocities, but according to simulations from Yaron et al., the velocity of the expansion increases with white dwarf mass. So it means that for the lower masses, you have the slower expansion velocities, which should be affected by more by friction. So there is something that we need to work in it based on physics that gives an explanation. So how does all this related to single white dwarf masses? Well, this model predicts, this is the same plot as before, and these are now the limits. Sorry, this is the classical case, the fully conservative case, and this is now our limit for stable mass transfer. And this is in the plane of white dwarf mass versus mass ratio. You see that all the systems here merge, and this should become single white dwarf. So we decided to see what happened with the simulations. If we simulate the white dwarf mass distribution for single white dwarfs, taking into account single stars and mergers, including our new model for mergers, we obtain that most of the low mass white dwarfs are descendant from cataclysmic variable mergers. We took into account two extreme cases, so when they merge, no one knows what happens with the secondary, so we took no accretion, so the whole secondary is disrupted, or full accretion, the whole secondary is accumulated around the white dwarf as a giant envelope. And in both cases, the main channel, it's in black, it's the CV mergers. It's the main channel towards forming low mass white dwarfs. And taking into account the observational biases from Tremblay, we increase these fractions of single low mass helium white dwarfs to 3.9 or 1.3, which is perfectly consistent with the observations. So these are the simulations from Tremblay and the observations, and they were missing these ones here that now we can reproduce that. So finally, I want to say something about ALMs because, well, Ingrid already told us that there are masses below 0.2, 0.3 solar masses that are extremely low and are normally found in very close periods until, this is because Joris Vos couldn't come. He was a postdoc until last month in Valparaiso, and he was looking for SDB stars with, it's the last one. SDB stars with in white binaries, and he found one that when he had the two lines spectroscopic binary, and he could constrain the masses, and he found that the mass of the subdwarf was 0.23. So it was not a subdwarf, was a pre-extremely low mass white dwarf, so an extremely low mass white dwarf still contracting. And he asked me to reproduce this system because the period was 700 days and something. So we tried and we couldn't make it except when we include a third object that was inside, like in a very close inner binary with periods between 1 and 3 days. And if the system merged according to our model. So you have the progenitor of the extremely low mass white dwarfs that fill the rotary from the Hertzsprung gap, so subgiant branch, and merge with a companion. And this merger produces the extremely low mass white dwarf that we see today. And the companion that is now at 700 days should have been closer, but at 100 days or so, so it was not involved in the merger process. So it's the only explanation, because it's the first extremely low mass white dwarf observed in a wide binary. So that's it. One more before it talks.
Ingrid? Okay, I'm opening for questions. Sylvia?
Hi, I have two questions for Monica. I was wondering with the enhanced incremental loss, this should also have consequences for the CV population, like higher mass loss rates or mass transfer rates, right?
Yeah.
Have you checked how it affects their luminosities, for example?
No, because we, in order to compensate this, because if we use the same normalization factors for magnetic braking, gravitational radiation, of course we get higher mass transfer rates, but we wanted to fit the mass transfer rate to the observed ones, so we reduced the normalization factors in magnetic braking and gravitational radiation to have the same mass transfer rates.
Okay.
So we fit that.
And the other thing I was wondering about the triple, if the outer orbit used to be smaller, rid from the white mass
Like
loss.
100.
And the initial orbit of the inner binary must also have been around 100 days.
No. The inner binary?
The inner binary went on the 0 sequence.
Was 1 to 3 days. Is the only way we can reproduce that. So that the progenitor of the ELM fill the Roche-Loff like at the very end of the main sequence of subgiant branch. So we found that the only possibility is that the initial orbit of the two main sequence stars was between 1 and 3 days, which is consistent with triples in general. So.
Another from Monica. In that merger case, are you assuming then that the secondary is completely disrupted and disappears?
No, we.
I thought your secondary is 0.3.
The secondary can be between 0.35 and 0.68, something like that. You can, but you well, what we put is that if it's accumulated around the white dwarf as an envelope, you don't accrete all this mass. So you generate kind of a giant, and then you can assume a maximum mass for the white dwarf that is from the initial to final mass relation for this total mass. Even you have the white dwarf mass plus the envelope, which is the companion, and then the maximum mass that the core can grow is given by the initial to final mass. But this is something that you have to test. This increases the mass of the ELM, but very few. So in fact, this is most is lost. Yeah. So this, in fact, this system is very nice to test what happened in the merger case, because it implies that you cannot increase the mass of the white dwarf too much.
Stefan?
I have a question for Ingrid. Your SDA main sequence population with that broke less than 0.9 solar masses, are those genuine halo stars? Are those the most massive halo stars we have? Or because from the top of my head, I know like 0.8 should be the turn-off mass of the halo. So, or are these blue strands? What is the idea?
Probably both things. Maybe you saw that I still have two populations over there. So what I think is that the blue one is the blue stragglers, and the other one are the single low mass. And well, the mass is a bit lower than 0.9. It's like 0.87 or something like that. And that's more or less the mass of the turn-off point for the halo. So I think they might be the most massive, but it's still agreeing with the theory.
Okay, thank you.
Keaton, and then Bart.
So for your number of, this is mostly for Monica, but relevant to both of you, I guess. For your number of isolated white dwarfs of 20 to 30%, I think you pointed at the ELM survey results for that, and the majority of those isolated white dwarfs are below 9,000 degrees. They're not distributed in temperature like the other stars, and I wonder if it's been suggested that those are also SDA stars that have the same sort of spectroscopic systematics, perhaps that place them there as yes, that's something.
So I don't know.
I guess the question is there a reason that would your model predict a cooler distribution of isolated low mass white dwarfs from this channel than the temperature
from the CV merger channel, you mean? No, we don't know what happened with the temperature of because in the merger process, this is something that we still need to simulate, and that I want to learn MESA to simulate this part, because the merger process is really complicated. So I think that maybe the temperatures are going to be higher because you have accretion. So, but if accretion doesn't reach the core, also the temperature increase doesn't last for long. So if they are all there, also they should be cooler. So to my experience, you need to simulate before trying to, because every time you try to guess, something strange happens in the simulations and it's not what you expect. So it's work in progress.
Bart?
I was just wondering also about that 20 to 30% number and whether we know that there aren't long binaries there? Because I'm just thinking about the hot subdwarfs. They were thought to be really long binaries, but now we know that there's a channel that seems to produce subdwarfs with binaries on hundreds of days.
Yeah, no, this 20-30% is an upper limit, of course. But
yeah, I think that one that has a wide companion indicates that there might be more. So
yeah,
we should definitely look for that.
But there are some singles, because there are some where you clearly see that it's not possible that you have really photometry that you see there is nothing. So if the period is longer than what you can detect, then you should see it in photometry, and you don't. So there are some singles, for sure.
Any more questions? One more question. You got it?
Ingrid, when you showed the distribution linear diagram of your SDAs, some, like very few, they were bang on in the white dwarf this community, in the white dwarf sequence. Why did we miss? Why did we? Is there anything special about this? Why did we think these were not normal white dwarfs? Why did we think these were SDAs?
Because they are really cool, so the lines are somewhat narrow, so they look like. Well, they are DA, but they have narrow lines. It's just that, yeah. So the spectral classification in the SCSS was wrong. Was just that. But they are in your catalog.
Okay, let's thank the speakers.
I'm sorry.
I did the same with the first
Yeah.
one, so don't worry.
Our next speaker is Joseph Senati, and he's going to tell us about the formation and evolution of hybrid helium carbon oxygen white dwarfs and their properties.
Thank you. Yeah, okay. Good afternoon. Hear me? My name is Joseph Zinetti. I'm a PhD student at the Technion from Institute from Israel. My supervisor is Chagai Peretz. I'm here to tell you a bit about the formation and evolution of the hybrid white dwarf. This work also done with Sylvia is here. So to understand what is a hybrid white dwarf and how they form, we need to understand the basic binary stellar evolution. So we're going to try to explain the formation of the hybrid white dwarf here. And as you know, the white dwarfs are composed mostly of electron degenerate matter and are divided into several types of white dwarf. For example, CO white dwarf and also the oxygen, neon, magnesium, and the final mass of the white dwarf is corresponding to the stellar evolution of the initial mass for the binary system or the single stars. The minimal, as you know, in the later decays about study of stellar evolution, the minimal mass through the stellar evolution of the single star is around 0.5 to 0.52 solar mass. So, however, the binary evolution could or can change this outcome and produced other types of white dwarf. Oh, sorry. Other type of white dwarf, and allowing to go to much lower mass of the white dwarf, as shown by Han in 2002. So, in interaction binary, the binary companion may feel its Roche law and maybe strip the helium or hydrogen envelope at in the RGB stage. But also, as you know, the evolution of the outcome for the binary evolution, it's strongly depend on the initial condition, for example, the initial mass and the semi-major axis. So if we take going to low mass, initial low mass binary, in particular, the wide dwarf masses of much lower than 0.45 are typically thought to helium wide dwarf. Actually, this work done by also Abin and Tutukov, or also Han, and also Elena is here. So all this study actually explored the very low helium wide dwarf. Our focusing is exploring the hybrid regime mass and their properties. So how actually they can form. So here is it. So in particular, also the binary evolution could produce a hybrid type of helium CO wide dwarf. So if we start with intermediate mass binary, the evolution of the binary, it's going like in the RGB phase, the hydrogen envelope is stripped following the formation of the helium core and the evolution on the RGB stage. And when the giant envelope is removed, the hydrogen burning shell is qualid, and the helium core keeps growing, and the star being to contract. But this is very important point, because that giving rise to helium stars. What I mean, that can be observed possible as SDB stars. But if the helium core is massive enough, above 0.32 solar mass, the helium ignition can be triggered, and the formation keeps going to a CO core. So far, we get a hybrid wide dwarf with CO core and thick helium shell. So, to produce the hybrid wide dwarf, we need intermediate mass binary and massive helium core as when we get the RGB stage. So actually, what we do, we're modeling this evolution by using MESA, actually binary MESA mode, and the single mode using by MESA. And here is some of the important initial condition that we modeled. For more details, you can find it in our paper. So all the models, we take solar metallicity, and let's see what we actually get in. If we're looking for the HI diagram, the finally stage, we're going to the degenerate wide dwarf. And here, what we see here, we compare the single mode and the binary mode for each diagram, following stripping the results. The configuration and the evolution is similar, so it's very important to our research. And if we need to know, or want to know which mass and radius the hybrid wide dwarf are, so here is we plot the mass-radius relation for 3 different temperatures for each regime of mass, the CO white dwarf and the helium white dwarf. And here we compare our result to PINI 2007, and we find actually, as expected, the hybrid radius actually it's between the regime for C white dwarf and the helium white dwarf, as you can see here. And here's a lovely hybrid white dwarf with other type of for white dwarf for the radius mass radius relation for the white dwarf. So the previous work was well done by Ibn and Tetukov in '85. Actually, the first they succeeded the very low white dwarf mass could be a helium CO white dwarf rather than it's a helium white dwarf. So it's very important to know that a previous work done and they get a helium CO white dwarf. So here's an example of, for one of our model. Here's the final mass of the hybrid white dwarf. As you see here, this is the helium, and this is a large amount of helium. So for all the model, you can see here the helium mass versus white dwarf masses, and the blue line is the fit linear for the range done by CBAR from the population synthesis, and the cross point is from MESA. It's very similar, except not include these 2 points, and we, in future work, we try to explain why this is not similar, but at all, the helium fraction for this range of masses, it's huge. So this is very important for different topics in astrophysics. So if we know how they form and when they form and what the rate of this type of white dwarf, so in particular, they form in the first 2 gigayears, as you see in the black solid line, and for a group of stars with initial mass of 1,000 solar mass, we accept 3.6 to 3.9 hybrid form in the Hubble time. And also, roughly 50% of the hybrid will merge. And the most important point, 14 to 31% for all these cases will merge with a white dwarf, other white dwarf. So here is so if hybrid white dwarf have a CO core and thick helium shell, so it can be play an important role in the transient event or the double detonation type as we discussed in the supernovae scenario. Here, what you see here is the flash simulation done by me and my supervisor, sorry. And here's the hybrid white dwarf merged with CO white dwarf, and maybe this can be give us a kind of thermonuclear event. So this is my summary. Thank you.
So we're having questions for Joseph now.
Okay.
No? I have a question.
Yeah.
Do you know what the proportion between carbon, oxygen, and helium are in the strip that you show? The proportion, percentage, how many of which?
You mean in the final white dwarf?
I mean in the population. How which are the you think are the most common that are going to form more easily?
You mean the rate between the CO white dwarf, CO and
in the intersection area? You have helium, you have carbon oxygen. If I see one starting with that mass, which core is more likely?
Actually, I don't know.
Okay.
I will. Okay.
Okay. Thank you.
Thank you.
Okay.
Yeah.
So, did you include rotation in your models?
Rotation?
Yeah, and how would that impact the parameter space where you would expect this type of form?
Actually, for the single mode in MESA, we didn't include the rotation. For the binary, yes, such of our model includes the rotation. But I think most of the rotation model not give us this thick helium shell. Okay, thank you.
Okay, thank you. Our last speaker today is Simon Joyce.
Okay.
And he's going to tell us about Series B and the gravitational redshift.
Not sure.
It's tricky. You can try your stick. That doesn't work. Microphone and pointer.
Okay, thank you. Thank you. Have you ever felt like when it's close to dinner, time seems to slow down and every second takes a bit longer than usual? So you get a very similar effect close to a white dwarf. So the gravitational potential of the white dwarf slows down time, and from our perspective, the frequency of light emitted from the white dwarf decreases. So the equivalent effect is that because the speed of light is fixed, the wavelength has to increase. So this is the gravitational redshift effect. This was actually proposed by Einstein as a test of general relativity. It was the third of the 3 classical tests that he proposed. But since general relativity has been pretty much tested to death since then, we can actually use it as a tool to measure the mass of a white dwarf. So what we need if we want to measure how much the spectrum has been shifted, we need a marker point, and white dwarfs provide this very convenient set of lines, which we can use as a marker. We particularly use the H-alpha line, which is this one here. And we know what the wavelength should be based on lab measurements. So when we take the spectrum of Sirius B, we can compare the two and see if it's been shifted. So we did this, and this was presented at the last White Dwarf conference. And we couldn't quite understand the result because the blue data points here are the gravitational redshift mass, and they didn't match the mass that we expected based on the orbit of Sirius B. And they also didn't agree with the mass-radius relation. And this is a big problem because we have really good data for Sirius. And as Jeff said earlier, you have to include Sirius B. So if there's a problem with Sirius, there's a problem with everything. Serious problem, yeah. It's not my joke. She did it. So to try to understand what was going on, we had a feeling that it was some kind of instrumental effect, but there was no way to kind of isolate how big the effect was. But we realized that you could come up with a new strategy. So rather than compare it to a lab-based rest wavelength, you could actually use the Hubble Space Telescope to look at Sirius A, which has a H-alpha line as well. And then you use that as the rest wavelength. So they've both been measured with the same instrument. And that should hopefully cancel out any effects that are just instrumental. So the idea was that we would try to look at Sirius B
and then move straight to Sirius A without changing anything about the instruments. But the problem with that is that normally if you move to a new target, you have to do a peak-up procedure, target acquisition. And we were using a very narrow slit, so that had to be done very accurately. But because of the different brightness of the two stars, you would have had to change the filter settings, and we didn't want to change anything. So in the end, we decided that we would just move straight from Sirius B to Sirius A without any target acquisition, which is is kind of the equivalent of shooting from the hip and hoping that your aim is true. So we were hoping we wouldn't miss the target, basically. Fortunately, I had a lot of help from Howard Bond. He was able to predict exactly where the two stars would be at the time of the observations, because he's done a lot of detailed work on the binary orbit. And so the red line over there, that represents the slits in the spectrograph, and we chose a particular date so that it would be orientated perpendicular to the line between the two stars. And so we just did this kind of blind offset. We moved from one to the other and hoped it would line up. So I was quite relieved when the data came back and we could actually see the H-alpha line rather than just a blank piece of sky. So you can see the top is the 4 spectra of Sirius B with the nice broad H-alpha line. And then the bottom of the Sirius A spectra with the H-alpha line, which is quite a bit narrower. So the next step was to measure the wavelength. So we measured the wavelength of each spectrum. So this is going from left to right. It's each spectrum measured in turn. So you can see the first two, it's Sirius B, and then we moved to Sirius A, took 2 more spectra, and then there's a slight change because we used a different position on the CCD. So that's some slight difference in the calibration of the different positions on the CCD. So we then moved back to Sirius B and then took a final spectrum at the original position on the CCD. That was to check if there'd been any change over the course of the orbit, because we thought maybe there's some thermal effects affecting the optical bench during the course of the orbit around the Earth. But as you can see, they all line up very nicely, so that doesn't seem to be a problem. So what we're doing is we're comparing the wavelength for Sirius A to that of Sirius B, and the difference is 1.71 angstroms. Sirius A, it will also be affected by gravitational redshift, but the effect is very tiny in comparison. So any difference between those two wavelengths should be just down to the gravitational redshift of Sirius B. There's 1 or 2 corrections that have to be made, because any movement between the source and the detector can produce the same shift in the spectrum. That's the Doppler shift. So we had to correct each spectrum for the orbital motion of the Hubble Space Telescope, because during the course of the observations, it's going towards and away from the target. And there was also a small correction for the binary motion of the 2 stars as well. So the results came out quite nicely. You can see the black dot is, or the black diamond, that's the new gravitational redshift measurement. So it lines up nicely with the mass radius relation. And if we zoom in, so the blue square, that's the dynamical mass, that's from Howard Bond. And then the green diamonds, that's the new gravitational redshift measurements. So they line up very nicely, and they also agree with the mass radius relation, which is the red line. That's the thick hydrogen layer line. The red diamond is the same gravitational redshift measurement taken with the different position on the CCD. So there's a slight difference there, but they're all compatible within the errors. So, so in conclusion, the new measurements seems to have solved the problem. It's compatible with the dynamical mass, and it's compatible with the gravitation, with the mass radius relationship. And it seems that the problem has been solved, so we can all enjoy dinner. Thank you.
Questions? Ingrid? Does this mass agree with the spectroscopic mass as well?
So the spectroscopic mass, we've been doing work on, the spectroscopic mass seems to come out a bit lower, but the error range is larger, so it is compatible. I did a paper on that that's just about to be published, so that's it is compatible, but there's still a bit of a question whether the spectroscopic mass needs a slight adjustment.
Martin? Go.
Sorry, I didn't look at whether you did or didn't account for the gravitational redshift on the series setting.
Yes, we did. We subtracted that away, but it's only about 0.5 kilometre per second, so it's quite small. So.
Some models of modified gravity predicts different relationships between mass and radius. Can you constrain that with your measurements?
I've never looked at that, actually. I'm not sure how big the difference between traditional gravity and modified gravity is, but it'd be interesting to see if we could. I'm not sure if it would be possible, because I think the best thing would be the dynamical mass. That's the best, the most accurate mass estimate that we've got for Sirius B. So I would probably use that one, but it'd be interesting to look at that.
Jeffrey in the back.
So what resolution were these spectra based off at? And is it enough to, for example, resolve the central core, maybe get enough upper estimate of the sign
Yeah, I think from what I remember, it's about 1 angstrom resolution, and then we used quite a narrow range in the core because we were concerned about stark shift effects. So we didn't want to use too much of a range that might be affected by the stark shift.
Yeah.
Sorry, what was the second part of the question? I didn't catch it.
Would you actually be able to do any type of upper estimate of these kind of that might be more?
Possibly, yeah. I haven't looked at that, but maybe we could have a chat now.
Last question? Okay, so let's go to dinner.
Yep.
Thanks. Wait, Patrick. There.
Only Patrick. I'm gonna put it up.
Okay, so we have a picture. There.